are going to see about a theorem on isomorphism in group theory. First of all, what do you mean by an isomorphism? We are given with two groups G and G dash. A mapping is defined from G to G dash. That is, F is a mapping from G to G dash, and the mapping should satisfy two conditions. The first condition is the mapping F should be a bijection, and the second condition is f of xy is equal to f of x into f of y. If our mapping satisfies these two conditions, then the mapping is called as an isomorphism, and the two groups G and G dash are called as isomorphic groups. So, f should be a bijection and f of xy equal to f of x into f of y. Two conditions. The first condition, f is a bijection, means our f should be both 1-1 function and onto function. So, 1-1 function means distinct elements in the domain must have distinct images in the codomain. Onto function means every element in the codomain should have a pre-image in the domain. Now, let us move on to the theorem. We are going to see about the theorem. Isomorphism is an equivalence relation among groups. So, now we are going to prove that the relation isomorphism is an equivalence relation among groups. What do you mean by an equivalence relation? Equivalence relation is defined on a set S as it should satisfy three conditions. The first one is reflexive, second one is symmetric, and third one is transitive. What do you mean by a reflexive relation? Reflexive means an element should be related to itself. Symmetric means if A related to B, then B also should be related to A. Transitive means we have to consider three elements A, B and C. If A related to B and B related to C, then A related to C. So, these are the three conditions for an equivalence relation: reflexive, symmetric and transitive. Now, we are going to prove that the relation isomorphism is an equivalence relation among groups. So, we have to prove that two groups are related to itself and two groups G and G dash to be considered. G isomorphic to G dash implies G dash isomorphic to G. And the third one is transitive law. So, we have to consider three groups G, G dash and G double dash. If G isomorphic to G dash and G dash isomorphic to G double dash, then we have to prove that G isomorphic to G double dash. Let us prove one. The first one, for any group G, Ig is the identity function G to G dash. But it is clearly an isomorphism. It satisfies the definition of an isomorphism. The two conditions also will be satisfied in this case. So, clearly G is isomorphic to G itself. So, the isomorphism relation is a reflexive relation. So, obviously we have proved the reflexive relation condition. The second condition is symmetric. To prove symmetric, we have to consider two groups G and G dash. So, let us consider two groups G and G dash isomorphic to each other. That is, G is isomorphic to G dash. We have to prove that G dash is isomorphic to G. So, we define F, a function from G to G dash, as an isomorphism. But since F is an isomorphism, F will be a bijection. Under the definition of an isomorphism, F is a bijection. Also, we know that if F is a bijective function, then F inverse is also a bijective function. So, F inverse defined from G dash to G is also a bijection. So, now we have proved that F inverse is also a bijective function. So, it is enough to prove the second condition for isomorphism alone. So, now we have to consider two elements x dash comma y dash in G dash. We define the mapping as F inverse of x dash is equal to x and F inverse of y dash is equal to y. So, when you bring your F the right side, it becomes f of x is equal to x dash and f of y is equal to y dash. Now, let us consider f of xy equal to f of x into f of y condition. This is the condition for the isomorphism. second condition. So it becomes x dash into y dash. Now once again, f inverse of x dash y dash becomes xy, which is equal to f inverse of x dash into f inverse of y dash. So we have proved the second condition for isomorphism also. So now f inverse is both bijection and f inverse of x dash y dash is equal to f inverse of x dash into f inverse of y dash. So g dash is isomorphic to g. We have proved that g isomorphic to g dash implies g dash isomorphic to g. Therefore, isomorphism is a symmetric relation. Now we have proved two relations. Isomorphism is a reflexive relation. Isomorphism is a symmetric relation. Till we have to prove that isomorphism is a transitive relation. So let's move on to the next stage. Let G isomorphic to G dash and G dash isomorphic to G double dash. To prove the transitive condition, we have to consider three elements. Here three groups. So we have considered G isomorphic to G dash and G dash isomorphic to G double dash. Now there exists an isomorphism F from G to G dash and G from G dash to G double dash. Two isomorphisms F and G. Since F and G are bijections, G circle F, the composition of functions G circle F, it is a mapping defined from G to G double dash. It also will be a bijection. Composition of two bijective functions is also a bijective function. So G circle F is also a bijection. Let x comma y belongs to G. We are going to consider two elements in the group G. Then let us consider G circle F of xy. When we remove the composition function, it becomes G of f of xy. But f is an isomorphism. So by the definition of isomorphism, f of xy can be written as f of x into f of y. So this becomes g of f of x into f of y. The next step, since g is also an isomorphism, we can split it once again. G of f of x into g of f of y. But what is g of f of x? It becomes g circle f. So once again it becomes g circle f of x into g circle f of y. So g circle f is an isomorphism. Therefore, g is isomorphic to g double dash. This proves the third condition, transitive law. So we have proved that the two groups are isomorphic to each other and reflexive, symmetric and transitive condition. Since the three conditions are satisfied, the isomorphism relation becomes an equivalence relation. Hence, we have proved that isomorphism is an equivalence relation among groups. Thank you.